Last problem in this section. So the motivating application for the derivative at a point, or the derivative at a point was slope at a point. That was our motivating thing that allowed us to we drew the picture with all the little tangent lines. That was our motivating idea, slope at a point. But there are other very common applications. Slope of a tangent line, which we've already talked about, instantaneous velocity at time x naught, instantaneous rate of change. Now, the words instantaneous, or the word instantaneous in both cases, is in parentheses because generally they won't say that. It'll say just velocity at 3 seconds or the rate of change at 5 seconds. When they give you a specific point in time, that is implying instantaneous. So the word instantaneous will generally not be there. They'll just give you a specific time. But whenever you read any of these things, slope of a tangent line, velocity at a time, rate of change of the time, all those things mean use f prime x naught. So those are key words telling you when to use this new thing called the derivative. At t seconds after liftoff, it should say the height of a rocket. Or it does say the height. I can't read apparently. At t seconds after liftoff, the height of a rocket is s of t equals 3t squared miles. How fast is the rocket climbing after 10 seconds after liftoff? So how fast? So it doesn't say velocity, but how fast does mean velocity. So we want the velocity at t equal 10, or we need to find f prime of 10. Now I'm going to call it f, even though it says s there. I'm going to call it f. And, because s's are just horrible letters to work with. S's look like phi's. But that's very common. This is called a position function, and very frequently position functions are s's, and then t for time. But you can change it to whatever letter you want. Let f of x equal 3x squared. Find f prime of t. So one more time, recall, f prime of x naught is the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. So in this particular case, f prime of 10 is going to be the limit as h goes to 0 of f of 10 plus h minus f of 10 all over h. And again, substitution would give you 0 over 0, which tells you nothing. So we need to do the algebra to get rid of that h. First step, f of 10 plus h. I just use my formula, replace the x or t, whatever you want to call it, with whatever's in parentheses, in this case, 10 plus h. Minus f of 10, which would just be 3 times 10 squared. So there's f of 10. And now we just start to simplify with the end goal being to cancel that h. So let's just start simplifying. Foiling that out, that's going to be 100 plus 20h plus h squared minus 300 all over h, which is the limit as h goes to 0 of 300 plus 60h plus 3h squared minus 300 all over h. Which is the limit as h goes to 0 of 60h minus 3h squared all over h. And then remember, we want to cancel at h. And you've got a couple options here. Since every term has an h, you can divide h from all terms or cancel h from all terms, whichever you want. Or we can do this. We can factor out an h in the top. And then cancel. And so we get the limit as h goes to 0. 60 minus 3h. Then we can substitute h equals 0. And so we get 60 minus 3 times 0, or 60. Now, being a math person, I don't stress on units very much. But if we read the original problem, I believe the original problem, let me pull this out and see what it said. The original problem said miles and seconds. So this would be miles per second. And there's my velocity. And so there is another application of the derivative. But notice, as far as calculating the actual derivative, we did it in the exact same way that we did the others. The only thing that changes each time is what particular little algebra you need to do to come up with that limit. But the algebraic goal for all these problems is to cancel that h. And that concludes this section.